Hello there and welcome to this episode. So in some previous episodes in the section where we focused on clock configuration, I mentioned a couple of times that there is this PLL engine that helps you to basically crank up the frequency at which your clock operates. And it can go as high as 180, 200. Actually, it depends on the kind of microcontroller that you are using or the microcontroller that is used on your dev board. And so in this video, we are going to concentrate entirely on how to get higher frequencies using the PLL engine. And if you're watching this on YouTube and you've not subscribed, please do well to subscribe and turn on the notification channel. Help me grow this channel so I can also reach a lot more people who need this quality content. Thank you very much. All right, so I mentioned that the PLL engine helps you to generate higher frequencies, right? Let me start by giving this caution again that just because you can run the microcontroller unit at a higher speed doesn't mean you have to do that. You have to take into consideration the power needs of your system, right? Because like I explained in some previous episodes, the higher the speed at which you operate the microcontroller, the more energy it uses. And so if you're running it on battery, then it's not going to last as long as you might want it to. All right, so we have seen this clock tree diagram many times, at least for the past 5 episodes. And in this particular video, we are focusing entirely on just this section. Of course, it feeds into everything that comes here, right? But you just have to understand what's going on here. And once you do understand it, translating it into code is as simple as ABC. All right, so the PLL itself is a clocking engine that helps to multiply. You know, here we are using devices or prescalers, and I mentioned that whenever you use a prescaler, you are basically reducing the frequency of the clock that gets into the input. So you step down the frequency from the input to the output. But the PLL has a divider and also a multiplier, and the multiplier there is what helps it to generate higher frequencies. At the core of the PLL is something known as a VCO, and I know all of these because I have read the reference manual and also a bit of the data sheet. You don't have to do that, but you can take what I'm telling you from this video. So there's a VCO, which stands for voltage controlled oscillator, and that is the core hardware component that does the work of generating higher frequencies from the lower frequency that comes into it. So this is the main PLL engine, and just like the sys clock, it doesn't have its own clock source, so it also depends on this multiplexer here. So this is PLL source mask, so it's a multiplexer that helps you to choose between either HSI or HSE to feed the main PLL engine. And because it's a multiplexer, you choose one and the other is not used, right? So in this exercise, we are going to use the HSE, but you can also conduct experiment and use HSI if you want to. Now let's try to understand how it works. So basically, what I have done here is I have selected that the clock source for the PLL engine should be the HSE, right? Now, before the signal gets fed into the PLL engine, you can see that there is a divider here or a prescaler here. In this case, we call it a divider because we want to step down the speed. Now, this also depends on the microcontroller. Some of them, it will tell you that, okay, the speed of the signal that comes in should be between 1 megahertz to 2 megahertz, and this is by design. And if it is by design, you have no choice than to obey it. The beautiful thing about this clock tree user interface here is that if I select anything, let's say I select 2, if it's a mistake and I put the mouse cursor there or the pointer on it, it's going to tell me. So it says PLLM, let me hover over it again. PLLM output frequency is currently set to 4 megahertz. It must be between 0.95 to 2.1 megahertz. So whenever it turns red like this, it means you are violating some design constraints in this particular sections of the clock tree, and until you fix it, you cannot really use this, you cannot translate this into code for the microcontroller unit to behave properly. In this video, my target is for us to configure the microcontroller to operate at 100 megahertz, right? So I am going to, it's always a good start. I'm going to let the speed that gets into the main PLL loop to be, main PLL engine to be 1 megahertz. So I know that HSE is 8 megahertz, right? From the reference manual and also the user manual and also the data sheet, I know that it is 8 megahertz that is coming in here. So if I want 1 megahertz, then I've got to divide it by 8. Right? If I want 2 megahertz, then I've got to divide it by 4. All right. The fact that I divided by 4 fixed this, but it broke something here. You should just be reading and then you know how to fix them. I'm going to divide by 8 here, and by dividing by 8, it means the clock signal that gets into the main PLL engine is running at 1 megahertz instead of 8 megahertz, right? So this is the divider. It is called M. This same name is used in the code that we write, so you need to note it. And in here, there is a multiplier. You see, this is X and this is dividing. So dividing means you are reducing, multiplying by a number greater than 1 means you are increasing, right? And so you can choose any of these multipliers here. And trust me, the VCO can actually take a small speed signal and bump it up a lot. So if it takes this 1 megahertz comes in, if I multiply that by 432, it means the speed is gonna be 432 getting outside, but that violates a lot of the constraints here. You can see that this HCLK cannot go beyond 168, and already we are at 400 and something, right? This cannot go beyond 42, and we are already at 400 and something. This cannot go beyond 84. So these are the constraints by design, and you have to respect them, otherwise you cannot get the processor to do what it wants to do. So I am just gonna multiply that by 200. I can also do 100, but that will not let me achieve what I want to do. Let's do 100, then you'll see what I mean. So I'm choosing 100 here. If I choose 100 here, you see there is also a divider. So look at it. There's a divider that reduces the speed that the clock enters the main PLL engine at, and then this multiplier here cranks it up to a very high value, and before it goes out, you have the possibility to also divide it to reduce it to a value that is fit for all the other downstream clock systems that are here. So you want to pay attention, right? Now I want to run this at 100, and if I check the P here, there's no 1. I cannot divide by 1, so it means my 100 can never get to this portion, and so I have to go beyond 100. That is why I choose 200, right? That is twice what I want, so I choose 200 here. And by choosing 200 here, it means the speed, the output speed from the PLL engine is now 200 megahertz, but I don't want to run the microcontroller at 200 megahertz. So what I do is I choose a prescaler here that reduces it for all the downstream clock systems. So if I can achieve the same 50 by dividing this 200 by 4. So you see there are multiple ways of achieving what you want. Now I want 100, so I'm going to divide by 2. Now this is M, is the divider before the signal gets into the PLL engine. N is the multiplier that cranks up the frequency within the PLL engine. P is the divider that divides the signal from the PLL engine before it gets out into the other mainstream systems. Remember that because we are using PLL, we first of all had to give the source that we want for the PLL, and then in the system clock max, which is also another multiplexer, we have to choose PLL because it is the output of the PLL, which is called PLL clock, that we want to feed into sys clock. Everything you are seeing on this UI has a one-to-one mapping to the code that we are going to write. Okay, so it gets in here. There's 100. The AHB prescaler is 1, so ACL is 100. And let's say if I choose this to be 2, I'm violating. So if I hover over this, it's going to tell me that the output frequency is currently set to 50, but it must be less than 42 megahertz, right? So then I go to 4. You just basically have to fall onto the next available prescaler to ensure that you are not violating any of these constraints. So look at the changes we have to do. We have to tell this PLL source max that we are going to depend on HSE as the clock source for the PLL engine. We have to indicate that the M of the PLL engine, or the divider of the PLL engine, is 8. We have to indicate that the multiplier within the PLL engine should be 200. We have to indicate that the scaling factor before the signal leaves the PLL engine should be 2. This one here, Q, it also depends. There are specific peripherals that get their output from this. In this particular case, it's not important, but you can see it tells us which of these peripherals depend on this. In this particular episode, this is not important, so we are going to leave it at the default. And then we have to set our AHB prescaler, APB prescaler to 4, APB2 prescaler to 2, and that's going to help us. So system clock is going to be 100. Some part of the microcontroller is going to run at 100 megahertz. The flash is also going to run at 100 megahertz. This is very important for you to note, because remember, the latency that you set for your flash memory should correspond to the speed at which it is running, and this is something we will have to check from the reference manual. And some other components or buses are going to operate at 50, 100, and even 25. Okay, so now let's come here and write our code. I have already written the code, but I'm going to explain everything to you line by line so that you can appreciate the one-to-one mapping. This you have seen already. So we basically start with the OSC init type def and the clock init type def, like we did. And then here we are just turning on HSC. So these two lines of code are turning on HSC because we need it to be the source for the PLL engine. Now this is where we do the configuration for our PLL engine. Now you see that I do osccfg.pll.pll state. So let's look at what this is. This PLL, it's a struct on its own. It is called RCC PLL init type def. Okay, now if we go in there, now I want you to develop this habit of control clicking on types to go in there to see how they are defined, right? So I can see that there's a PLL state. All of these are just integers because at the end of the day we are configuring registers. We are not doing bare metal yet, that's why we are not seeing this, but everything here is an integer. And then there's the PLL source. This is where we choose the particular source in the PLL multiplexer. This is the M, that is the division factor for the PLL VCO input. So VCO is what I talked to you about, that it is the voltage controlled oscillator, right? So the M here, the PLL M, divides the signal before it gets into the VCO as the input clock. And then the N is the multiplication factor. So this is where the cranking up happens. And then the P is the division factor for main system clock. So this is where we divide to scale it down before we send it to the system clock. And then the Q here, I told you that specific peripherals use it. So the OTG file system, SDIO, and RNG clocks are the ones that use this. We are not going to touch this yet. All right, so this is why when we access the PLL field on the OSC init type def, we have to do another dot to get into the actual fields of the PLL init type def. So we say PLL.PLL state is RCC PLL on. So we are turning on the PLL engine, like, hey, I want you to turn yourself on so you can crank up the frequency for me. And then again here we have to specify the PLL source, which is which of the clock sources or the oscillators is going to be the source. So we say RCC PLL source HSC. So this is the line that is saying this one here, this guy here. Okay, this selection here is what I'm talking about. So here we are saying that the source is gonna be that, and then we are configuring the M, the division factor, the multiplication factor, the division factor before it goes out. All right, and then I am also I have changed the prescalers, so it was 1, 4, and then 2, as you can see here. So it is 1 here, 4 here, and then 2, right? So there is a one-to-one mapping, like I said, from what you see on the UI and the code that you write. Now, something very important is I have had to change the flash latency to flash latency 3 instead of 0. And you might wonder what will happen if I don't do that. Well, I will demonstrate that for you to see. But as to how I found that information, you just have to open the reference manual and search for the flash latency table. And here I can see that it says the wait state should be 3 or 4 CPU cycles if my HCLK, so the HCLK clock speed, is between 90 and 120. In our case, I know that my speed is 100, and so 100 falls within 90 and 120, so I need to set the flash latency to 3, and that is why it is 3 here. So I'm just gonna is there any other change we had to make? Nope. So yeah, the last change was here, the clock configuration sysclock source. You need to tell sysclock that its source is gonna come from the PLL clock. So that is also this line here, this line here. Okay, this is what you are doing in that piece of code. So now I'm just gonna build this project. I'm not generating code. Let's see the output in case anything fails. Okay, so one warning, it's just a warning about this line of code here. So to prove that we have set it to run at 100 megahertz, I have gone ahead to use this function, which you have seen many times. How RCC gets sysclock frequency. I'm just getting the sysclock frequency to confirm that it's 100 megahertz, right? So let's debug. And I'm waiting for the debugger to start so we can see what value the system clock frequency currently is after running this code. So at the moment, you can see that sys clock frequency is 0 because we haven't executed the clock configuration and we haven't read it, right? So I'm going to step over. So HAL init has executed, system clock config has executed, and then now sys clock frequency has been read, and you can see here that this is 100 megahertz, which is also 100 million. Now let me stop this. Let's change the flash latency to the previous value, which was 0, and let's see what's gonna happen. So I just changed this to 0. I'm going to build this project again. Nope. So you see, the problem here is it builds all right, but it will not run. If the flash latency is not set properly in your firmware, then it's not gonna run. So let's see something. If I try to run that particular part of code, it's going to throw an exception. Okay, so I step over, HAL init executed, system clock config executed, and boom, this is an error. Now you see, it's so hard for you to even understand from this error message. You never know where you went wrong, right? And this is why, as a firmware developer, you need to develop the habit of reading your reference manual and also making sure you obey everything that is recommended. Don't forget that this is information that is coming from the manufacturers, and so it is in your own best interest to do what they say you've got to do. They designed it, they know the flaws, they know the limitations, and you have to observe it. Thank you very much once again for watching this, and I will see you in the next video.